Hello, my name is Orion Ehrlich, and today I'll be presenting about how to find the golden ratio in pentagrams and other interesting mathematical properties of the pentagram. To begin, let's talk about the components of a pentagram and how to make one. So a pentagram is simply made of one regular pentagon, which, as we all know, is a five-sided regular polygon, and five isosceles triangles with angles shown in the picture. To draw a pentagram, you start with the regular pentagon and then extend all the edges out until they meet at points, and you're left with a five-pointed star. So now we want to try and identify all the unique lengths that make up a pentagram. To begin, we can see that the longest length would be side A, and that goes from the tips of two opposite triangles. Side B is the side of a triangle and an edge of the pentagon. Side C is simply the edge of the pentagon, and side D is the long sides of the triangles. So in total, there are four unique lengths that make up a pentagram, and they decrease in size, starting at A being the largest, then B, then D, and then C. So before we try and find the golden ratio in the pentagram, first let's remember what the golden ratio even is. So like pi, the golden ratio is also an irrational number and can also be represented by a Greek letter, in this case, phi. The golden ratio can be described as the ratio between the long and short sides of a rectangle, such that if a square is placed next to the long side, the new rectangle that is formed will have the same ratio of side lengths as the original rectangle. And you can see that in that picture below. If we start with the original red rectangle, which has side lengths b by a, and add on a square with side lengths a, it forms a new rectangle with side lengths b plus a and a. And the ratio between the original rectangle and the new rectangle's side lengths will be equal to phi. And we can find an exact value for phi if we plug in some values for those letters and then rearrange it to get x squared minus x minus 1 equal to 0 and solve using the quadratic formula to get 1 plus or minus the square root of 5 over 2. And there's two values that we get from this, and the negative value actually has the exact same decimals as the positive value, and therefore has the same irrational properties as phi, but we generally talk about phi as being the positive value because it represents a ratio of two positive numbers, and therefore should also be positive. So now let's try and find phi in a pentagram. If we draw a pentagram and put c equal to 1 and then measure what all the side lengths would be, we immediately notice that d is equal to phi, which is quite interesting. If we look at side b, we notice that the decimals are actually the same as the decimals of phi, but it has a 2 in the front instead. And this actually makes sense geometrically if you look at the picture, because side B is the side of a triangle and the edge of the pentagon, and is also just equal to sides C plus D, and D is equal to phi, and so B is just phi plus 1. So that makes sense. But it's not clear what that number A represents. So let's explore a little bit further. If we take the ratio between sides A and B, we notice that that is equal to phi. So now let's look at the ratio between B and D. That's also equal to phi. And the ratio between D and C is also equal to phi, which is quite interesting. So let's see if this holds true for different side lengths. If we take C this time to just be some random number and then measure what all the other side lengths would be, this time we can't see any obvious relation to phi. But let's look at the ratios again. If we look at the ratio between A and B, B and D, and D and C, we again notice that they're all equal to phi, which is pretty cool. If we look at the ratio between A and C, we see that we get the number that we didn't recognize before, which was the length of A of our original pentagram. B and C has a ratio that's equal to the side length B of our original pentagram. And D and C is simply the ratio equal to the reciprocal of phi. So from these two examples, we can now state something about the pentagram. It appears that the ratio between one of the unique lengths of the pentagram and the next shortest length is always going to be equal to phi. So the ratio between A and B the ratio between B and D, and the ratio between D and C is all equal to phi. Now let's try and see where else phi can be found in a pentagram and what else these numbers might mean. If we look at the squares of phi, we see that phi squared is equal to length B of our original pentagram. Phi cubed is equal to side A, and phi to the fourth is a number we haven't seen yet, but it might show up later. So therefore, when side C is equal to 1, D is equal to phi, B is equal to phi squared, and A is equal to phi cubed. Now let's try and explore a little bit further by adding a second pentagram inscribed inside our original. Here you can see that the outer pentagram has the same side lengths as our original one, where C is equal to 1 and D is equal to phi. And our inner pentagram, if you notice, has some similar numbers. This time B is equal to 1 and A is equal to phi. But something more interesting happens if we start to look at the ratios between the same unique lengths of the inner and outer pentagrams. So if we look at the ratio between A2 and A1, or B2 and B1, C2 and C1, or D2 and D1, they're all equal to the same number. And this is a number that we've seen before. If you remember from the previous slide, this is equal to phi squared. So now we've discovered another interesting place where phi can be found. Let's see if this pattern continues. We can start by drawing a pentagon around our original pentagram, and this will give us a new side length, C3. And as we just saw, the ratio between C2 and C1 is equal to phi squared. So what would be the ratio between C3 and C1? Well, it turns out it's a number we've seen. It's equal to phi to the fourth. And because of all the ratios were true for the previous two pentagrams, we can assume that this would hold true if we continued out and drew another larger pentagram. So the ratios between A3 and A1, B3 and B1, D3 and D1, and as we saw, C3 and C1 will all be equal to phi to the fourth. And this would probably continue if we drew a smaller one inside or continued out drawing larger and larger pentagrams. So now let's try and find some other interesting mathematical properties of the pentagram. To begin, we can look at the Fibonacci sequence and how it relates to the golden ratio. The Fibonacci sequence is simply a sequence of numbers where each value is equal to the sum of the two previous values. And it can be modeled by starting with a 1 by 1 cube and then placing a 1 by 1 cube next to that, and then drawing a new cube with a side length equal to the long side of the rectangle formed by those two cubes. That would give us a 2 by 2 cube. And then if we continue out, we'll get a 3 by 3 cube, then a 5 by 5, then an 8 by 8, then a 13 by 13. And this can be continued on indefinitely, where the side lengths of each of the new cubes will be equal to the values in the Fibonacci sequence. And if we look at the aspect ratio, which would be the ratio of the side lengths of each of these cubes that are formed, we can see that it starts to approach a familiar number, phi. And even just by the 8th step, where we have 34 divided by 21, the approximation of phi is already very, very close. And if we continue out farther with larger Fibonacci numbers, the approximation will get even better. So if we draw a new pentagram, this time with side length C equal to 13, we can see that all the side lengths that we measure are all equal to the following numbers in the Fibonacci sequence. So D is 21, B is 34, and A is 55. And they all have some decimals after them, but there's a 0 first after the decimal, which means it's a fairly good approximation. If we look at another Fibonacci number, this time we set C equal to 233 and measure what all the sides would be, we get, again, the following numbers in the Fibonacci sequence. We get 377 for side D, 610 for side B, and 987 for side A. And this time there's 2 zeros after the decimal, which means it's a very, very good approximation. And this is because we're using a higher value in the Fibonacci sequence. If we continued on with higher numbers, the approximations would get even better. So let's see if this pattern still holds true for our original pentagram. If we go back to the one where the side length C is equal to 1, we can see how this pattern still holds true for the most part, but the approximation is not nearly as good because we're using the smaller values in the Fibonacci sequence. So D could be approximated as 1, B could be approximated as 3, and A could be approximated as 5. But again, the approximations aren't as good because we're using the smaller values. So finally, let's talk about the golden spiral. This is a famous spiral that can be seen all over the place in nature, and nautilus shells and pine cones and sunflower seeds. And it can be drawn in a similar way to how we created the Fibonacci sequence. But instead of starting by one cube, you start with a rectangle where with side lengths that have a ratio equal to 5. And then you add a cube that creates a new rectangle so that the side lengths still have a ratio of 5 and continue on. And if you connect the edges of all those cubes, you'll get the golden spiral. And it turns out you can do the same thing with the pentagram. And the interesting thing about these spirals is they will stay symmetric no matter their scale, as long as you continue the pattern indefinitely. So today we were able to see some very interesting properties of the pentagram. We were able to find phi in the ratio of the side lengths, and find how if you set side C equal to 1, that all the other sides will be different squares of phi. We've seen how if you inscribe smaller ones that the pattern holds true, and even found the Fibonacci sequence hidden within the different lengths of the pentagram as well. So it just goes to show you how interesting and beautiful math can be, and how perfectly it can go together with geometry. So thank you for listening to my presentation. Here are some references, and if you're curious at all, this picture is one of the models I created in order to make all the drawings in this presentation. I don't really know any drawing or photo softwares, but I'm very familiar with SolidWorks, and so I made all the drawings from engineering drawings in that program, and I was also able to get exact side lengths, so thanks to the Smart Dimension tool. So anyways, thank you.